Greetings, everyone. This is Jeff Wilkerson, Professor of Physics at Luther College, bringing you the next in our series of what to look for in the night sky. We're talking about the week of June 26th, 2023 this time around. So what do we got going on this week? The last couple of weeks, we've looked at Venus and Mars, and Venus stops its approach to Mars this week. It sits almost the entire week. It sits about 3.5 degrees away from Mars. So in the evening sky, any evening you go out to look west, you'll see Venus shining brightly. You'll see Venus well before it's dark enough to see Mars. So you wait around a little while, you'll have a chance to see Mars above Venus. And remember, one finger is about 1 degree at arm's length. We're going to use that a lot today. So about 3.5 degrees from Venus is Mars there. And they'll keep that separation for this entire week. And then starting next week, they'll slowly start to separate again. So we'll keep an eye on that. The other thing that's going on this week, the moon starts the week just a little over half full and approaches full by the end of the week. So we got a lot of moonlight. So we have to, if we want to observe something, the galaxies we've been talking about this spring, not a good week to be observing galaxies as the moon slides right through that region of the sky, Virgo and Leo, that we've been exploring, and there's just way too much moonlight to see any kind of galaxies like that or anything faint. So we're going to turn our attention to the Cygnus region of the sky and just look at some stars. So we're going to enjoy Venus and Mars hanging out right next to each other. We're going to appreciate the moon filling out a little bit each night as it heads toward full. And we're going to look at the summer triangle. Looks something like this. These things are not at all to scale. The summer triangle looks something like this. 3 bright stars. It's up now as it gets dark. It'll be a little bit, it's not on the meridian yet, it'll be a little bit east up directly overhead, but you got Vega as the leading star up here, a big bright white star. Deneb is the tail star. Remember, we've talked about this before, an Arabic word, Deneb, that means tail, and this is tail of the swan, Cygnus, right here. So Cygnus stretches down into the summer triangle. Altair is the southernmost star down here, and Aquila the eagle. And so we've got this big summer triangle hanging high overhead, rising into, by midnight, it's way up high in the sky. And those are the 3 bright stars that you see in a hazy summer night hanging up overhead. But let's look at Deneb, is the Vega, we wrote over here, we want Deneb, is the tail of the swan. And the swan stretches down the river of the Milky Way, and that's the wings of the swan, sometimes called the Northern Cross as we look north there. And so we see that stretching this direction. This is Albireo, shows up right here in the middle of the summer triangle. Albireo is one of the most famous double stars in the sky. You have a small telescope. Point that small telescope at Albireo. Deneb is the alpha star, the brightest star in Cygnus. Albireo is the beta star. So Albireo is a nice big bright star you see here in the middle of the summer triangle. Point your small telescope there and you get a beautiful blue star and a beautiful gold star aligned right there in your field of view. If they're actually a binary system, my guess is they're not. If they're actually a binary system, they must be very widely separated and very slowly orbiting. And we haven't seen any motion between the two. My guess is one of them's further away than the other. We don't really know whether they're an associated pair or not, but it's a very widely separated pair if they are a binary system. So you got this beautiful blue and gold stars. You're not going to see a better, more beautiful binary system than Albireo. It's one of the most famous, not really binary, paired stars like that, double stars. And so one of the most beautiful double stars in all of the sky. Now, actual paired binaries that are orbiting around each other, this is easy to split, beautiful. A couple that are harder and more challenging, if you like that kind of challenging. You step out the wings of the swan this direction. That's the head of the swan, the tail of the swan. There's the wings. You step out the wings of the swan past Epsilon and on out this direction. You get to Mu. And Mu is, remember, the faintest stars are about 6th magnitude, 5th to 6th magnitude that you can see with the naked eye. And so this is right on that limit. You can see it. If you got a good dark sky, no problem at all. 4.5 magnitude. And it's a really close binary star. These stars are actually orbiting around each other. Get your small telescope out and give it a try. See if you can split Mu into 2 distinct points of light. As you move back up this direction, you're going to run across Tau up here. Tau is a 3.7 magnitude star. and it's right in there. And so it's a little bit brighter than mu. You can step up. This is Epsilon Cygni, and you can step up from Epsilon Cygni and mu that direction to find tau. And so tau is right here, and it's also a fairly challenging binary star to split, but a good binary for you to look at. A little bit brighter than fourth magnitude. So that's a star you'll see shining more brightly than the other stars in this region around it will be tau right there. So get your telescope out, see if you can split these, find Albireo, enjoy the beautiful show that Albireo is, and then find these two that there's no doubt we can see the orbits. We no doubt they're orbiting around each other. See if you can split those into individual stars. Now, next to tau is a very interesting star. Only about 2 degrees away from tau, headed back toward the middle of the constellation right here, is 61 Cygni. 61 Cygni is about a 6th magnitude star. So it probably, you can see it with binoculars, no doubt about it, but there's going to be a lot of other stars about that brightness around. And so you're going to want a finder chart or something to try to help you make sure you're seeing 61 Cygni. Or you can locate it within a couple of other stars. See if you can find a finder chart. Draw yourself a sketch of what the stars should look like in that region. Get your binoculars out and look to see if you can find those stars. Reproduce what you see in the binoculars on a piece of paper and see if it matches the sketch of the region of the sky that you were looking at. And you've got 61 Cygni right there. What makes 61 Cygni so much fun to go out and look at it? And I like to just go out and try to find it and sit and look at it for a little while. So what 61 Cygni, we knew it was close. And one of the reasons for a long time, to go back, we're going back hundreds of years now, we knew it was close. And we knew it was close because it has one of the fastest proper motions of any stars in the sky. That is to say, like to think the stars are fixed, and they are more or less fixed relative to one another. The pattern of Cygnus will be the pattern of Cygnus for quite a long time, for as long as I need to think about it. I'm going to see this pattern of Cygnus. But what happens is the stars are moving a little bit relative to one another, and the closer a star is, the more likely it is to be moving noticeably against the other stars. If you imagine, here's you looking at the stars out this direction, 2 stars that are moving the same speed, and one that's much further away has a much smaller angular speed. It moves a smaller distance. We see the angles across the sky are what we see something move, right? We're not seeing linear velocity. We're seeing how fast of an angle it is to move from this point to this point. We measure that angle, and we have an angle per time, and we call that the angular velocity. But 2 stars that have the same actual physical speed through space have different angular velocities. If one's twice as far away, it has twice as slow an angular velocity. So to see one really zipping across the sky means that angle it moved was faster, in the same amount of time, means it must be pretty close. And we knew that for 61 Cygni. We had tried for a long time. The other thing that we think about that works like this, as we orbit the sun, and we move from one side of the sun to the other, foreground stars tend to shift back and forth against background stars. We see this star over here, and then we see this star over here. So we see nearer stars jump back and forth, and we call that parallax, or trigonometric parallax. From the time of Copernicus into Galileo, into Kepler, into Galileo, into Newton, we knew we were orbiting around the sun, and we should, if there are stars that are enough closer than background stars, we should be able to see those stars jump back and forth. And the universe is so big. That's what makes this such a fun observation. The universe is so big that the foreground stars are barely moving back and forth against the background stars as we orbit across here. And it took us centuries to find it. It took us actual centuries to locate the first parallax. And Bessel did this in 1848, I'm going to say, something like that. Go look it up, see how close I got. But Bessel actually saw that in 61 Cygni. He was the first one to find evidence of parallax in the stars. And by that time, when we started the process, it would have been a test for the Copernican model, the Galilean model, the Keplerian model of orbits around the sun. By that time, we had little doubt that was a better model than stuff orbiting the Earth. And what we do use it for now is it actually measures the distance. You know your geometry. You do a little bit of geometry right here, a little bit of trig, and you can calculate the distance to that star when you see how much it shifts back and forth. If you know that distance, the radius of our orbit, for example, the semi-major axis of our orbit. So we saw that star jump back and forth. Bessel found that in 61 Cygni. So hard it was to find this trigonometric parallax, this stuff jumped back and forth. It took, by the time, 50 years elapsed, and we still only had a handful of stars we had measured that parallax for. And so this is a great, purely geometric way to measure distances in the universe. It's a really robust way, but it was a challenge to unfurl and to be able to do this. And today it's the first step on the cosmic distance ladder. We measure distances to stars with trigonometric parallax, and we use that to calibrate distances to those stars to find other techniques that allow us to see further into the universe and further into the universe and further into the universe. And so that history, our understanding of how big the universe is and where we are in the universe started with this measurement of parallax to 61 Cygni. So go out there, find Albireo, find Mu, find Tau, see if you can split those double stars, those binary stars, and then just hop over a couple of degrees from Tau to 61 Cygni, right at the edge of naked eye visibility if you've got really good dark skies. See if you can find 61 Cygni and think about that history of our starting to understand where we are in the universe and just how big the universe is. And that's what we got for you, something a little bit different than we've done before. So a little bit of a change. Hope you have a chance to get out and do some observing this week. Hope you have clear skies, but a little bit of rain if you need the rain. And as always, thanks for watching, everybody.